Okay, so here's a typical closed system example. I have a tank filled with R134A. So there's keywords you got to pick up on when you're doing these sorts of problems. Rigid. So rigid means um, volume is constant. The total volume is constant. So the volume at the beginning of the process is going to be the same as the volume at the end of the process. All right, so that's what rigid. So it contains R134A. The initial pressure is 160 kPa, so P1 equals 160 kPa. And quality, given the pressure and the quality, so it's the mass is 40% in the form of vapor and 60% in the form of liquid. Okay, so then we transfer heat to it until the pressure reaches 700 kPa. All right, so the first thing we're asked to find is the mass. This is another one of those things which seems like an impossible question to ask or to answer initially, but we'll go through it and we'll see that it's actually not that difficult. So um, if you remember, we've talked about this before, but if I have an extensive property and an intensive property, um, the quotient of the two can give me the mass. That's always the case, just by definition. All right, so the mass is equal to the total volume divided by the specific volume. It's also equal to the total internal energy divided by the specific internal energy, or the total enthalpy divided by the specific enthalpy. If you have one or the other, or if you have both, say you have access to the total volume and specific volume, it's the same as having access to the total and specific internal energies and so on and so forth. All right, so that's another way of calculating the mass. So we can calculate the mass, let's say for the initial state. I have two intrinsic independent properties for the initial state, so I'm confident that I'll be able to calculate all of these values, in fact. But I have direct access to the total volume that's given to me in the problem statement. So I'll just take the mass to be equal to the volume at state 1 divided by the specific volume at state 1. And so that's going to be 0.5 meters cubed from the problem statement. And then the specific volume is going to be equal to the specific volume. So I use this is the notation I use, as a function of pressure. So it's reminiscent of the syntax for ease. But so the pressure equals 160 kPa, and quality equals 0.4. Okay, so the specific volume at state 1, when I go into my calculator, is 0.0498 meters cubed per kilogram, which is roughly, I mean, for all intents and purposes, that's 0.05 meters cubed per kilogram. All right, so 0.05 meters cubed per kilogram. So the total mass of R134A in the tank is 10 kilograms. Now, so really I calculated for state 1. Specifically, I calculated it for the initial state, right? I used the initial properties. However, um, the mass isn't going to be entering or leaving the tank, so I know that M2, this is also going to be equal to the mass at state 2. And I can also derive from this the fact that the volume doesn't change. So I was told that the volume doesn't change and the mass doesn't change. So the specific volume can't change. All right. So I know that the specific volume at state 2 is going to be equal to the specific volume at state 1, which is roughly equal to 0.05 meters cubed per kilogram. All right. So those are some observations I've made so far. Not necessarily directly applicable. It will be here in a second, but some things that you needed to pick up on in order to answer the rest of the questions. All right, so B. So the simplified energy balance comes out to so here's something maybe you haven't seen before, but it follows directly from that. So delta U is just U2 minus U1. These are capital letters. So the change in internal energy of the system is equal to the, this is just a simple fact, that it's equal to the internal energy at the final state minus the internal energy of the initial state. All right. And then just by definition, that's the mass times the specific internal energy minus at the final state, and the mass times internal energy at the initial state. Here, let me get rid of that. Okay, and then factor out the mass, and you just get U2 minus U1. All right, so I beat that horse to death, I think. All right, so in this particular problem, we have no work interactions at all. So these are necessarily going to be 0. And heat is being added to the system, and we haven't been given any information about it being pulled from the system. Now, in real life, it's hard to say that there'd be no heat escaping, so you could take this as being the net or something to that effect. But if you're not given information, you could treat it as if you're not given any information about, don't overthink it, okay? If you're not given any information about heat escaping the system, assume that value is 0. Unless there's some other way of calculating it or something like that. If you're not given any information sufficient to calculate that the amount of heat escaping, say, any one of these variables, then the answer is 0. Sometimes you'll be given information and it may be hidden a little bit, so be careful when you're canceling these terms. But in this particular problem, heat is being added to the system, and we're not allowing for heat to escape. Okay, so this whole thing simplifies to so I'm given some properties of the system and some energy interaction. All right, and so I'm asked to find what is Qn. Okay, so I know the mass. I already know the mass, but I don't know U2 or U1. U1 is easy. I can just use the same independent intrinsic properties I was given it in order to find the specific volume back in part A. So U1 is going to be equal to the internal energy as a function of the pressure and the quality. And I go into my calculator, and that comes out to be 107 kilojoules per kilogram. All right. Now, U2, I have to read into the problem a little bit, and I've sort of preempted this, but I know, what do I know about state 2? I know the pressure. I'm given the pressure. And I have to do a little bit of thinking to find out what other property I have available to me. But because I noticed we have a rigid tank and the mass remains the same, the specific volume remains the same. All right, so I know that the specific volume at state 2 has got to be equal to the specific volume at state 1, which is equal to so now I have two independent intrinsic properties, and I'm able to calculate the specific internal energy at state 2. And that comes out to 377. So that's the trick on these problems. There's usually, you know, enough information given to fix the state at state 1, like explicitly. So I'll give you the pressure or the quality, or the pressure and the temperature, or the pressure and the specific volume, or some way of calculating it, or something to that effect. So this will be given pretty well explicitly, or one of the states will be given explicitly, pretty close. But then you're going to have to use some intuition and some knowledge of the system in order to sort of infer the second property for the final state, or for one of the states. Okay, so there's a little bit of thinking that has to go involved, that has to go into fixing the other state. All right, but then once you have the two states, pulling the information out is pretty straightforward. So I have the mass, it's 10 kilograms, and now I know the specific internal energies. I just do that math. And Q in comes out to 2,700 kilojoules. All right, and then C. So if I have these states in this process plotted on a diagram expressing, pressure versus volume, specific volume. So let's start with state 1. All right. So how did the pressure increased? The pressure increased from 160 to 700. So I know state 2 is going to be up here somewhere. It went up. And then I know that the specific volume is the same. The specific volume. So I'm going to have a vertical line plotted on this diagram. So this is 1. And the exact placement's not important, but just understanding the fact that if I plotted this process on a PV diagram, I would get a vertical line.